Today we're going to look at the tangents to an ellipse. Here's an ellipse centered on the origin. Such an ellipse has a formula x squared over a squared plus y squared over b squared is 1, and a is the semi-major axis, and this is b, semi-minor axis. Well, it happens to be this way because I chose it like this. I could have made the long side along the y-axis. It wouldn't make much of a difference. Now let's take a point. I'll take it over here, x0, y0. So this point is on my ellipse. So the question is, what's the tangent line on this point here? There's a nice drawing of it. So I'm looking for this tangent line. What is the equation of tangent line t? What do I mean by that? Well, canonical equation for a straight line is Lx plus my minus 1 equals 0. So what I have to do here is find L and M. And one way to do this is by implicit derivatives. And I think this is the easiest way, but I'll show you another way later on. Let's make some room here. I will consider that my y is a function of x, and x is an independent variable. And so this function here, x squared over a squared plus y squared over b squared minus 1, this can be considered, if I set this to 0, it can be considered as a definition, an implicit definition for y. And like usual, I find my derivative, 2x over a squared, plus, well, I have to differentiate the inside and outside of this here. So that's 2y of x, y prime, x over b squared, and the minus 1 is 0. So here I can solve for y prime. And there we have it. This is the slope at every point along the ellipse. That's pretty good. That's a very effective formula, because now at x0, y0 point, the slope, well, I know the slope, it's minus b squared over a squared, x0, y0. There we go. All we need to do now is plug that into the equation of a line. So the general equation for a line going through point x0, y0, that's y minus y0 over x minus x0 equals the slope of this line, but the slope is minus b squared over a squared, x0 over y0. Doing a bit of algebra, I get this. All right, and I can rearrange these things and bring it all to one side, like so. Okay, that was all just algebra, elementary algebra. But now let's notice something. These two terms here. Well, here I can use the fact that the point x0, y0 is on the ellipse. And so this must be true if those 2 points are on the ellipse. Okay, so I can combine these two and they become 1. This plus this is 1. And then when you consider the minus in front, you get a minus 1, and then you move that minus 1 to the other side and you get a 1. And we are done. We can now write this a little bit more like our canonical form of a line. x0 over a squared x plus y0 over b squared y equals 1. So this is my L, x plus m, and this is my m, y is 1. There's my equation of the line. Let's use these results to plot the tangent envelope around an ellipse. I did that here with my graphics program Asymptote. Let me show you how I did that. So the first thing I did was plot an ellipse with a is 5 and b is 3. That's easy to do in Asymptote because the geometry module has a lot of ellipse drawing stuff. So now I do this substitution, and my xk and yk, these points xk, yk are guaranteed to be on the ellipse no matter what angle theta I choose. And you can prove that for yourself. What you can do is substitute these things in this formula and you should get 1. Then what I did was I chose a bunch of angles. I started with 10 degrees and kept adding 6 to it, 22 degrees and so on. So I build all these little points. You can see them, almost see them, tiny little green dots. Those are my xk points. All right, so then I draw the tangents at all these xk, yk points. And you remember I used the tangent formula, which we just derived. And I just plotted these things. Asymptote has lots of line plotting functions too. And I get this beautiful figure, tangent envelope. Why don't you try creating it in your favorite programming language? I'm sure you can do this in Python with matplotlib. Believe it or not, it's possible to do all that without calculus, with just plain old algebra. We can find the tangent given x0, y0 point on the ellipse, but we can also do it the other way around. Given that this is a tangent line, find the point that it's tangent on. Well, we can solve both of these using just algebra. First, let's consider some facts. What are some ways that a line can interact with an ellipse? Well, the first way is this. There's no intersections, but then we also have this. These are two different intersection points. So here I have a value for x, and here I have another different, distinct value for x. That's kind of interesting. But what's most interesting is the next case. Here I have what appears to be one intersection point. Okay, but actually it's not really one. Let's imagine it this way. Take this point here and move it. Take this point here and move it. Well, it's going to move. If we move this line, these 2 points will get closer and closer together. Finally, they become very, very close. Here, actually, on my figure, you can't see this clearly. They're actually 2 points very, very close together. And so we can imagine we continue this process. What we'll have is 2 points on top of each other. And that's exactly at the moment of tangency. So what we have here is actually 2 repeated intersection points. And I will call the x-coordinate here x0. I only have one x0 here. But I have, in principle, 2 points, you see. So with this concept, we will be able to solve our problem. We just need to keep this in mind, that the tangent line is very special. It lies on a repeated point. Let's start by solving this problem here, and as a consequence, we'll automatically get the solution for the first one. Okay, so that goes like this. Given that this line Lx plus my is tangent to the ellipse x squared over a squared plus y squared over b squared, well, find the point of tangency x0, y0. So what we can do is we can start by finding x0, and then, well, we'll plug in x0 into something. We have a lot of formulas here, and we'll be able to easily find y0. So our first job is to find x0. From the equation of the line, we can solve for y. And then what we do is we take this and put it in here, and we get a big equation for x. Well, doing all that algebra gives me this, but now I have a quadratic equation in x, and I can call this my a, and this coefficient is my b, and this coefficient here is my c, and I can find a solution, 2 solutions for x using quadratic formula. It's a lot of algebra, but the final result is really elegant, so it's worth doing. So I bravely go forward and solve for x, and I get this beautiful formula. Now, let's call this thing inside the root, let's call this big delta. Like so, and in terms of delta, I can rewrite my solution for x and make it a little bit more elegant. There, very good. Now, I have 2 solutions, but like I said before, I don't want 2 solutions. I want a repeated solution, and that happens when this delta is 0. And so the repeated root happens when x0 is a squared L. Very beautiful. Now let's find y0. There's the equation of the line. Now let's put in the x0 that we just found. I get this, and from this I can get an expression for y0. I get this. Oh, what to do next? Well, I have this here, and I know that delta has to be 0. So if delta is 0, I can now write this answer for y0 very easily, because from delta 0, I have 1 minus a squared L squared is b squared m squared. So that's b squared m squared over m, and that's b squared m. Wow. So this is really something. Okay, look at the symmetry of this. X0, Y0, my point of tangency is a squared L, b squared m. Now, I'm sure some of you or most of you have seen stuff about tangent lines to conics, but have you ever seen this? Given that a certain line is tangent, what's the point of tangency? Well, there you go. Here are the line coordinates, L and M, and here are the semi-axes of the ellipse. So that's a totally amazing and beautiful solution, I think. All right, now let's solve it the other way around. Given that you know this point, x0, y0, what are the coefficients here in this tangent line? Well, that's really easy to do because I can equate these coefficients. I can write x0 as a squared L, and from this I immediately get L, a squared, and y0 is b squared m, and from this I have immediately the solution for m. And so my tangent line equation looks like this. Okay, very amazing. I really like this with and without calculus. It was amazing. How about an exercise? You try it for other conics. In particular, how about the sideways 2px, the sideways parabola, where p is some number. Try it for other ones, like maybe a hyperbola. And plot the envelopes. Yeah, plotting the envelopes. That's a great project if you're into Python and matplotlib. Why don't you try that? Okay, so like, comment, and subscribe. Send me a super thanks if you liked this video. And I will see you next time with cool and interesting mathematical stuff.